Раз, два. О, тут чути? Окей. О. Але він давно працює. Окей. Now this sound goes to Zoom, right? Oh, great, great. Okay. There is reverberation still. Haha. Finally. Now, what do we mean by network? In very general case, so something that have vertices and edges. So formally, as we will see in a few moments, it is built on a set theory. So set of vertices or nodes, set of edges or links. But now let us talk in terms of attributes of network. So how do you describe network structure? Well, one can note that it's not too hierarchical. It's not too hierarchical. It has more important nodes, less important nodes. And again, it's not purely regular nor purely random. So it's something in between. And well, that makes it interesting. It can have many levels, or it can be more evenly distributed in terms of links between nodes. Sometimes it reveals the hidden structure. And as we will see, there is a very nice case of voting in parliaments where you put link if two parliamentarians vote for the same for the same question in the same way, and you can see the hidden structure of political groups. And there are several cases of such revealing hidden structure. And what is really nice, networks are natural for complex systems. And I had to put this slide here about complex systems because this subject of complexity is most hot nowadays, multidisciplinary subject. And again, no one can tell you strictly and define what is a complex system, which is studied in different fields in physics, biologies, because every one of you is a complex system, and your brain is a complex system, and your body is a complex system. Universe is a complex system. So networks themselves, this is something that naturally describes such systems. And again, they have you can define it just attributive. They have just following properties. So they usually have emergent phenomena. It's the thing where you have the sum of parts is more than it's more than mechanical sum of parts. So the sum is more than just mechanical of sum of individuals. There are emergent properties in a complex system. There are critical transitions and nonlinear feedback loops and so on. So all the different complex things we see in life, we see in the universe, and so on. So we will often see that networks are used to describe such systems. Okay, now where do we meet networks? Actually, it's hard to find a field where you cannot find this kind of structures. So telecom, internet, social networks. So our phones, smartphones, telephones, mobile phones some long time ago, it was also called cellular phones because of cells, which makes a coverage of plane the most effective, and they make up network, social networks, sure. So this is a kind of links between second grade students who befriend who, and you can see there is some very popular persons, less popular in peripheria, and so on. Sure, transport networks, it's very practical field where you have to put the hubs, the nodes in the place they are most effective. Sure, biology and neuroscience networks. Again, our brain is a network with a very, very large number of nodes and links between them. Percolation problem and discrete topology. So it's more mechanical field. And I know there are material scientists here and chemistries. And also in this field, the network analysis will be useful. Semantic networks, networks of words and maybe conceptions, notions, maybe thoughts. Okay, you can make from this also a network. And my favorite, the large scale structure. So this is a slice of cosmological simulation, and well, our eye, human eye, can naturally recognize a network here. Though in universe, the galaxies are not linked directly one between others. They're just one near the other. Yet, so this network is like imaginary, right? But yet with a network analysis, as we will see, we can explore more intense these structures. We can find new knowledge if we just imagine that galaxy each to other are linked and they form network in this way. Okay. So everything started in 18th century, and the father of mathematics, Leonhard Euler. He was the one who found the first problem in graph theory and start developing this theory. The bridges of Königsberg, you know, the beautiful German city temporarily occupied by Russians, but I hope it's not over. The bridges of Königsberg, there are 7 of them, and there is a river, and Euler asked himself, is it possible to cross all the bridges in one walk, all the bridges, and in this special way, to each bridge to be crossed only once and only once. So you have to cross every bridge, but you can do it only once. So he made a scheme of bridges, and he actually proved this is impossible. And this is because properties of edges and properties of vertices and edges of this network, graph or network, it's synonyms. So you see the foundation was set in 18th century, but interesting thing that the most development this field obtained in the 20th century. So the set theory, the calculus, everything was developing fast, but when the right time came, the graph theory also became a very important mathematical field. Okay, so as I already mentioned, the strict definitions for graphs that you have two sets. one set of vertices, and second set is a set of pair of vertices, or actually the edges, or links, lines. And uh, well, so we here in this course, in these lectures, we will keep just to the simplest possible way to construct the network. That means that our networks will be, our graphs will be simple, because you can have multiple edges between two nodes. Then it's called multigraph. It's not simple graph. You can have loops. Again, we will not consider such kind of graphs. The graph can be directed, where you have directed links. So in this example, the A is connected to B, but B is not connected to A. Again, we will look only at non-directed graphs, and the graph can be weighted. So, for example, here the edges have the weights, but it also can be that vertices have the weights. And then, well, maybe it's very useful for some transportation problems. Famous problem of traveling salesman problem. Задача комівіаджера українською, так? Traveling salesman problem, which is actually still not solved in general case. There is only some approach with heuristic methods. But again, it's already very interesting, this every case, but it will make the theory more and more complex. So we'll keep to the simplest non-weighted, non-directed graph. Okay, connected and disconnected is simple. So if you can go from each point to any point in the graph, then it's connected. If it is broken into subgraphs that are not connected, that is disconnected graph. Next, so again, simple terms, complete graph is a graph where each node has connection with each. So it's all possible edges are there, are present in a complete graph. And regular graph, it's a graph where all the nodes have the same degree. So degree is number of edges that come into a node. Or so all in regular graph, all nodes have the same number of neighbors. So we can say that two nodes are neighbors if they are connected with a link. Okay, some more definitions. Bipartite graph. So it's often useful to have graph where they can be split in two parts. And well, the definition is that if you can split in the way that nodes from one part are connected only to nodes from the other, then it's called bipartite graph. So also you can see that when you draw a graph, you can do it in different ways. And here is the example of isomorphic graph. So you can redraw the connections in a way that it became a bipartite. Okay. So, and also another kind of important kind of graphs is a planar graph. So this one can be transformed into these three cases, and this makes him planar. This makes this graph for vertices graph planar. But you cannot do it with a complete 5 vertices graph. There is no way you can redraw it to be a planar graph. So the planar graph is the one where the vertices, the edges cross only in vertices, right? So here first you have this cross section in the center of a square, but you can redraw it. For five vertices graph, it is impossible. So if it's complete, it will never be a planar graph. Okay, and now what we are talking about to this moment, it's all basic notions of graph theory, and this is why the synonym to the complex network is a graph theoretical approach, graph theoretical method. And sure, graph theory is a huge field in mathematics, but as we will see, well, we are not going to dive deeply inside, just examples of theorems in graph theory, for example. Well, this is simple and still important. The number of the sum of degree of all vertices is twice twice the number of edges. So it's a very basic and important result. And well, one of the consequences is that the number of vertices with odd degree is even in any graph. And one more example of graph theorem, that's bipartite graph, that graph with least two vertices is bipartite if and only if it contains no odd cycles. Okay, so cycle is again something very intuitive to define. It's literally the cycle between the vertices. Okay, so you can, there is this link here where the graph theory is given in a very simple words and simple notions. Some questions for you. Okay, even we can start even here. So how many edges a graph with n vertices, a complete graph with n vertices have? It's a question from combinatoric, actually. Yes. How many? Yeah, correct. So combinatorics is tightly connected to the graph theory. And okay, it's a correct answer. Now, more difficult questions. How many edges in bipartite graph with n and m edges in each parties? So just for your to think for you in a break, and more question. Yeah, so you have bipartite. One part has n vertices, second one have m. How many edges in a complete bipartite graph with different number of edges? And okay, maybe you can also quickly answer the second one. What is the largest complete planar graph? So yeah, so if you have already 5 vertices in your graph, then if it's complete, it cannot be planar. But now already with these definitions and theorems, you can see how to prove it strictly, mathematically. And okay, now for the following questions, you will also have to introduce one more definition notion. This is actually face of a graph, but still, what is condition of existing and of Euler path? Euler path in graph is the one that originally Euler was thinking about, how to go through each edge, sorry, for each point, each node of the graph, but never go twice through any of it. But you have to visit each node. So this kind of path is called Euler path, and it's well, sure, not any graph contains Euler path in it, But you can come up with a condition that guarantees you that Euler paths exist. Okay, so and one more interesting question. Again, you have to deal with faces. Actually, for the third one, you don't need faces. You don't need just condition on a number of edges for each node. But for the last one, you will need a notion of face. But still, you can imagine. So face is something that is contained by the edges. Now, if I will tell you only the number of edges and number of vertices, can you tell me if the graph can be redrawn as planar graph? So you can sure say that if it's complete, for example, complete 5 and more nodes, that's sure it's not planar. But if it's not completed, I just give you a number of vertices, number of edges, and okay, number of faces of graph. Can you tell me, is this graph planar? Yeah, sure. Yeah, you know the answer? Okay. Yeah. Yes, correct. Yeah, I guess you had a course of of graph theory. It's called Euler characteristics of a graph, and yes, you have combined them exactly as you tell me. Okay, good. One more important thing. Uh, just a moment. Just have to track the time. Now we finish at what time? Um, okay, good. Uh, Now, important things for us, it will be the representation of graphs, representation of networks. So the very popular spread way is to represent the networks through adjacency matrix. Uh, Important thing is that adjacency matrix is a sequential representation. This means that you have first to put numbers of your on your nodes, and then to build this matrix. This is not very good actually, because you can I don't know, you can change the numeration, start to numerate your nodes from other end, and then the adjacency matrix will be different for the same node, which is not very good. But still, it's very useful. So how do you build it? Uh, you put okay, if you have unweighted graph in, for example, you put on a your matrix will be number of nodes by number of nodes, and you put 0 if they are not connected, where the crossing is, and you if they are connected, then it's 1. So again, uh, it's easy to build this kind of matrix, but cons negative side is that if you will have an empty network where a very few number of links, then the matrix still will be very large. And okay, so but people already have all the wow, it's a failure of my computer. Okay, I just had a blue screen of this. Okay, it will reload itself, and we can talk about adjacency matrix. So it's not because of antivirus, don't worry. But I have enough to reconnect. Sure, yes. Yes, I think yes, it is, but uh, we will not. Okay. I'm not connected, or am I connected? No, I'm not. Just a moment. So yeah, there is a way to, I think there is a way to represent uh, the network in this way, uh, but well, it's not a matrix, and with matrices you can have all the algebra, all the multiplying, adding things, and your GPU can work with matrix. So I never okay in papers in works I never saw other representations than adjacency matrix. Uh, okay. Oh wow, that's really interesting. Thank you for sharing. So it's embedding kind of representation. Uh, yeah, just 2-3 minutes to Zoom to load. Uh, but what is the twist in my lecture now? That now I'm going to say, so the graph theory is good, okay, but it's not what we are going to study and to consider here. Okay, now I am online and I'm going to share the screen. Just a moment. First time this kind of blue screen failure during the election for me. Okay. Oh, yeah. Okay. Now, how about this? Yeah. Uh, come on. Come on. Okay. Okay. So now, okay. A similar way of representation is a indents matrix representation, where you have now a number of vertices by number of edges, and you put one and zeros whether if the edge connects to two nodes. But it's really similar, and okay, you will almost never in a complex network analysis you will find something else besides the adjacency matrix representation. So obviously, if you have weighted network weighted graph, you just put numbers, not zero and ones, and okay, and we will have kind of centralities, kind of characteristics of network based on adjacency matrix, so it's important. Now, come on. Okay, now one more important thing that we were talking about weighted and non-weighted graphs. For non-weighted graph, you can still measure distances between the nodes. So, okay, by the way, for weighted graph, you can have weights of edge and you can have weights of nodes. Maybe you can have even both instantly. But we keep to the simplest one. And for non-weighted graph, you can measure distance between the nodes by the pass, by the nodes you have to pass through to get from one to each another, from one to another. So here's a simple example. Sure, can be multiple way to go from B to C, for example, but you have to select the shortest one. So in this example, the distance between all the nodes is equal to 1 because it's complete graph. Yeah. So you have to do only one step, and you can go from B to anyone to any neighbor, any node. But the interesting fact here is that you can measure distance even if your edges are not weighted. Okay, and the final slide about graph. So this is examples of famous, interesting, intriguing problems in graph theory. Some of them are solved, for example, with the four-color theorem. So, you know, that now it's proved that there is a way to color your map using only four colors in a way that no two adjacent regions have the same color. And it was proved recently in 21st century, and it was proved by with help of computer. So it's a computer kind of brute forced the all possible ways of coloring different maps. And first, because there was too many cases, too many possible ways, the mathematicians first didn't accept the proof, but now it's regarded as proved theorem. And well, the five color was proved in 18th century, long time ago, and the four. So it's first it was known that you have to have not more than five colors with this to have this no adjacent regions with the same color. And now it's proved that you have to have only four colors, which is cool. Yeah. So if you remember in your old maps of the world, they were actually four colored, and now it's proved that any kind of lines of borders, it's enough only four colors. So another problem is finding the clique. So the clique is subset of vertices that are complete graph. So the clique is part of graph which is fully connected. It's totally connected. Each part of the graph is connected to each node is connected to another. And now this problem is, as I remember, is proved to be NP-full, and but there is no general algorithm how to find cliques in the graph. And again, travel and silence problem, how to find the shortest path with the shortest spending of fuel, or just the shortest path if you have any distribution of your nodes. And again, maximum flow problem. So if you have, for example, two cities and small towns between them, and you have a commute road, for example, by railway, you have to build your flow in a way. So the trains, for example, from one city to another would get the maximum number of people. So it's a general problem which has no general solution. Heuristics is everything for this kind of problems. And it's all related to the graph theory. Okay, but graph theory is good, but it will tell you nothing in general cases about the structure and hierarchy in a network. And well, we started from the thing that it's important. It's important to we are interested in a inner structure of network, and so it's too much math in graph theory, and also it's often either too many numbers to characterize, or too little. So it can tell you whether the graph can be planar or not. So just some general knowledge about your graph, which is not enough because you are interested in the structure of the network. So the solution is to compute network matrix. Now, and in general, the complex network approach is all about these things, network matrix. So now we'll go through the most popular ones, and you'll see how it works. okay, there are two types of networks: local ones, where when you compute the metric or the characteristics, call it how you want. So local for computed for each node, and global computed for all the network. The idea is when you work with local individual metrics, the idea is to compute all of them and then to look at the distribution. So because when you compute some metric for all the nodes, you will have just a bunch of numbers, and to deal with them, you will have to look at the distribution. Sure, the maxima and minima will give you the most important, or the most important nodes in one way or another, but the most interesting will be to look at the ensemble, the distribution of the nodes. So, and with this, for example, you can come to the comparing the networks, because the famous, okay, the obvious problem, you can have non-identical graph, non-identical networks, but still very similar. And there is no way to compare them just node by node, because you have very large number of nodes you can have. But by comparing this kind of distribution, you can catch the idea of how one network is similar, how much one is close to another. And okay, you can also, to say something about structure of the matrix, of the network, you can compute the correlation, cross-correlation of different metrics. Okay, so the simplest one, the degree of node, the number of edges that goes inside and outside of the node. Sometimes it's a normalized degree of node. They divided by the squared number of nodes. So interesting fact that you can describe the graph, the network, with a degree sequence starting from the largest one, but it's not a unique description of the network. But well, almost any analysis of a network will start with computing degree nodes and looking at distribution, looking at the maximum of degree, the most connected node, and you can infer some information just looking at the distribution of the degree. Next is clustering coefficient, which is also simple, has simple definition. Now, yeah, let me this picture. It's well, it's complete graph of 4 edges, and it have a clustering coefficient 1. And now, if you want to compute the clustering coefficient in general case, you just have to find triplets. So a node that is connected to 3 other nodes, and then ask how many of these 3 neighbors are connected, how many edges are between them. So for this blue node, you always have this triplet, 3 neighbors, but in some cases they are all connected between themselves, and in some cases they are connected only through this blue node. So this case is if they are fully connected between themselves, if they make complete subgraph, or as I say, a clique, then it's the clustering coefficient is equal to 1. If they are disconnected and connected only through this blue node, then it's clustering coefficient 0. And you just count the number of edges and divide by 3, because there are 3 of them. Okay. Obviously, if you have more than 3 nodes, for example, 4 or 5, you will have to look at each triplet. And for each triplet to compute the clustering coefficient and then take the average. Well, it is important metric because it gives you a hint if the graph tends to cluster together. For example, we can have a network which has high degree, but high average degree, but the links are distributed in a way that it's almost broken into separate cliques. Then it will have a high clustering coefficient, and this is actually not very good connected network. Closeness centrality, it's more complicated. So as we already know, you can find distances between nodes in terms of neighbors between two nodes in its shortest path. And well, in this approach, you can find the most central node, which will have the least it will have the least reciprocal of the sum of the distances to all other nodes. And this is called closeness centrality. Well, it is what it is named. Just give you the most central nodes. Not always they will have the highest degree, but they are sure important because from them to the periphery is it's the kind of shortest path to periphery is from them of the network. Another kind of centrality is betweenness centrality. Now this will tell you for a given node how many shortest paths pass through the node, and it's different from the closeness centrality because the node can be far from all the other nodes, but it can be crucial for example, connecting two parts of network which is well connected between themselves, but have a few links between them to inside. There can be subgraphs that are complete or well connected inside, but poorly connected between themselves. And the betweenness centrality, high betweenness centrality nodes are kind of transport hubs where, or I don't know, airport hubs where all the roads go through them. And yeah, so here's the algorithm of computing betweenness centrality. You have to find how many shortest paths go through your node and to normalize it by all the paths that go through your node. Okay. Now, sure. Yeah, sure. That's a good question. But as I remember, so here's the sum that you do not, so you don't have to have coincidence. Okay, you cannot count distance between two nodes twice, right? But okay, can you repeat again? Yeah, but yeah. Okay, as I remember, you select the unique path. So the several shortest paths between two nodes are counted as one shortest path. Yeah. Okay, now generalization of the degree of the node is called alpha or Katz centrality. So it's simple one. You can count your neighbors, and then you can count neighbors of your neighbors and sum them up, but with some coefficient, and then count neighbors of neighbors of neighbors, and again sum them up, some added to the sum, but with the square of the coefficient alpha, which is less than 1, between 0 and 1 usually. It's a small number, something like 0.01. And in this way, you can, how to say, generalize the notion of degree. It's like degree of all the levels, right? And here is a comparison between Kac centrality and degree centrality for the same network. And you can see that degree centrality will give some score for nodes that are, well, not center in at all, but they have some links. While Kac centrality will give even higher score for most central ones, and the peripheria is peripheria, so it's the lowest values of Kac centrality. And for this, actually, you can write the definition through the adjacency matrix. Yeah, you have powers of this matrix and summation with a coefficient that will reduce the importance of of neighbors if they are far from you. This is important centrality because okay, so it was introduced in the mid of 20th century, but it often is more useful than just degree. And probably most important of all of them, okay, one of most important is eigenvector or just eigencentrality, which is something similar, but okay, so here's it's computed iteratively. The first step, you give each of nodes the rank of 1, and then you go through this algorithm where you compute the number of neighbors for each node. Okay, and you add not the number of neighbors, but you add this eigencentrality itself. And so you recompute the first time, and then second, third, and so on. And just at some point you stop. And what you get is eigenvector centrality, eigenvector, because it can be rewritten with adjacency matrix in this way. And so it's a so the values of eigencentrality is eigenvector of the adjacency matrix in some power. Okay, so why it is important? The Google Corporation, when they tried to find the way to show the most important pages to the viewer in the highest in the very first results of search. So they find that papers with the highest eigenvector centrality were the most suitable for the viewers. So how do you usually build a network of between the pages, between the internet pages? One page can reference to other, and this will be a link between pages. Yeah, it will be directed graph, but still. And it appears that eigenvector centrality suits the best when you are looking for most important pages on the internet. So PageRank algorithm is based on the eigenvector centrality. This is interesting fact. Okay, so just an example of network to see the difference between different centralities. You can see, so you can have all different highest betweenness, highest closeness, highest degree, and highest eigenvector centrality. And this shows that your different networks give you different perspective of your network. And this is advantage of computing many characteristics, many metrics. You are looking at your network from different angles, from different sides. Okay, and another picture is just distribution of values of different metrics. So harmonic centrality is kind of version of closeness centrality with different normalization. And you can see that, okay, there is some important part of network here in the upper right corner, but it's important in different ways for different centralities. Okay, so I have still 12 minutes. It's good. Maybe a little more because we have a dilation. Few words about global metrics. Most simple and important one is density of network. It's just simply the normalized number of edges, normalized by the number of all possible edges. So you divide number of edges by the number of edges in complete graph with the same number of nodes. And transitivity of network is something related to clustering coefficient, as I already explained. So it's reciprocal to the global clustering coefficient, which is actually just averaging over all the nodes. So more clustered in clicks network is worse in transition. So it doesn't have this kind of transition hubs, transition nodes, and it have lower transitivity. I didn't put the exact formula, but it's literally reciprocal to the global coefficient and clustering coefficient. Okay, and another thing you can characterize your network is a largest connected component. So not always, as you will see, not always your network will be connected. You can have disconnected subgraph, and the largest connected component is something that characterizes you. For example, you can in numbers it can be percentage of the all nodes that are included in this connected component. For example, largest connected components can consist 50% of all nodes. And it's important characteristic of your network. And the last one, the assertivity of the network. Usually this metric is associated with some another characteristics. For example, again, with the degree of nodes, and it will tell you what is the tendency to cluster regarding this matrix. Whether the nodes tends to cluster high with high degree, or on contrary, high with high degree nodes with low degree nodes. So you can see, for example, the assortative way of clustering on the left, this assortative on the right. Here only, so here the clustering are between, the connections are between high, only between most probable only with between high degree nodes, and here they are more random or mass. But okay, well, it's have more complicated definition because it have to take into account the distribution of these characteristics. For example, degree. Okay, now what can we do with all of this? With all this kind of metrics, kind of characteristics. So we can now quantitatively talk about networks in terms of this matrix. So you can look at a distribution as an average numbers of matrix, as a deviation, standard deviations of matrix, and so on. And now, before we go into some real cases, we also should consider some modeled networks. The rule of generating such networks are really simple, but as it occurs, we can find examples of such simple networks, modeled networks in nature really often. Random network, we will look only at the way of modeling in a random way. So usually you have a number of some fixed number of nodes, and for edges you have some distribution to be linking two pairs of nodes. It can be Poisson distribution, power law distribution, and so on. It is important to study random networks because you can you can compare something that you modeled to something you observed in nature or in any field, and you can compare them with a matrix we just introduced, and say that the process that give birth to such kind of network was this kind of randomness. For example, this can be this way of inference. Now, the most famous is sure Erdős-Rényi model. Can be defined in two ways, but okay, let's consider one of them. You have a fixed number of nodes, and then you have probability P, and the probability, so the probability to of two nodes be connected has the following way. So it's Poisson distribution. Sorry. And the so authors Erdős and Rényi, they introduced this kind of random network in 1960s, and with such simple modeling, they have shown that you can say really a lot about the network, depending on the numbers n and p of generating numbers n and p. For example, for example, with this condition, graph almost sure have no connected components of size larger than logarithm of n. When np is equal to 1, then graph will almost sure have largest component of size of the n to the power of 2/3, and so on. So this is how it looks, how this kind of networks looks. So it's really simple case when you have just some number of nodes, and then you randomly throw the edges between two random nodes. So it's already here. It can be seen that at some number of some value of probability, something interesting emerges inside the network. For example, this large connected component, largest connected component. There is kind of how to say critical phenomena when you steadily increase the probability of nodes to be connected, and at some point you have emergence of really large subgraph that connects a really large portion of your nodes. So this is this emergent behavior which we talked before. And here's distribution of degree of Erdős-Rényi model, and it's compared to the Barabashi-Albert model, which we'll talk about in a minute. So, okay, but we can say it's by definition this distribution would be expected. Now, all another kind of model, but again, it's also generated model, is a Barabashi-Albert model, where the generating is has a following rule that you add a node and you add the edges that connect to the other with probability increasing to the nodes that already have high degree of the node. So you add the node and you expect it to be connected to already big hubs, to already high degree nodes. This kind of generating is called Barabashi-Albert model. You can see it's contrary to this randomness of Erdős-Rényi model, and so it's a general two classes, large classes of random networks, and it has totally different degree distributions, usually power law, and this is also what is called scale-free model. Why? Because the Barabashi model doesn't have this emergent behavior where you have transition, some critical phenomena transition from when you increase the probability of connecting the nodes. So the Mathieu effect is present in Barabashi model. So the larger probability to be linked to the high degree nodes. The high degree nodes became more and more higher and higher degree when generating new nodes. And what is interesting is that the Barabashi model is typical for human societies. Friendship, science-based citation, transmutation roads. This is something what we call the unfair world problem. So the world is unfair. The richer become richer and richer, and the poor remain poor. But this is how human society works. So, but sure, usually our attempts are to break this model in a human society. Okay, and the last slide I think for today is about small world network, and again this is kind of type of networks that have this following feature. It's characterized by high clustering, efficient, and low distance. So distance is in terms of number of nodes between in your path from one node to another, and this is how we would like to have our human network. So we would like, and it looks like we really live in this small world network where you can count handshakes from, I don't know, from me to Joe Biden or Volodymyr Zelensky or whatever, and it appears that it's not tens or hundreds of handshakes. It appears there are some crucial hubs, very important nodes that help us find very shortest path to not obviously distant nodes. And well, I hope that this school will make the small words of Ukrainian scientists smaller, but in sense that we will be more connected. Yes. So well, another interesting feature is that when you grow the number of nodes, the shortest path grows only as logarithm of the number of nodes. Okay, so I think that's it for today. And if you have any question, please ask. Yes? Yeah, so what I meant is that we as astrophysicists, we are sure that matter is gathered in galaxies. And okay, there is some hot gas between the galaxies, but there is nothing like a transportation road from one galaxy to another. They actually just neighbors or not neighbors. So they just, in very simple way, they just uh, cloud, cloud of points, right? Point cloud. And we um, we built the network as just in our imaginations. That we introduce this algorithm by ourselves. So we say, for example, they are connected if the distance between them is smaller than certain number. It's called linking length. We're going to talk about it tomorrow and maybe on Wednesday. So, but there is this value of linking length. It's not written somewhere in the universe. We came with our ruler to the large scale structure with our human ruler, and well, this is the rather disadvantage of this method, that you have to introduce some parameter to build the network from the point cloud, right? Uh, and the persistent homology method that Vitaly was talking about here last summer, they kind kind of overwhelms this disadvantage by regarding all the possible linking lengths. But complex network method is about the structure, not about the scaling, but about the structure of the network. So yes, so it's kind of imaginary network, but still, it's you will see it's useful to consider it. Yeah. More questions? Yeah. Sure. Yeah, but think of this: the gravity is kind of scaleless because okay, it had a 1/r² law, right? Uh, it's proportional to 1/squared distance, and so it's kind the you will feel the gravity of the really some heavy nodes, some heavy halo or galaxy cluster very far away, right? And so yeah, you can, for example, you can introduce the weighted network. You can put the real weights to these nodes, this cluster of galaxies. But the problem is that usually when you observe the universe, you know these numbers, these masses. You know it is very approximately. You're not sure how many matter is there, and what the motion you see, it's not enough to reconstruct the masses of the nodes of the galaxies. So this is why I think we will um, we will have this as our practice case, and we will not use the network will be unweighted. It's simpler and it still gives you some interesting results. Okay, more questions? Yes. In what? Oh, yes, in machine learning. For example, and we really did this. You can have the values of your matrix as input for training some model, which will, for example, I don't know, find the connection between network metric and some physical characteristics. For example, um, maybe not mass, maybe star formating rate, something from the real world, from observation, and maybe in, I don't know, in other cases, I don't know. So you can form your input data matrix uh, from this evaluated values of network matrix. And you can train to predict something basing just on your matrix, which is useful because to compute them, you have to have very little information. Actually, just coordinates of your nodes. If you building the network based on linking lengths, for example, you just have to the coordinates of the nodes, and you compute the matrix we discussed, and then you feed it to some machine learning model, and then, for example, for each node, it will tell you, for example, I don't know, mass, velocity, spin, or whatever, which you didn't give to the which you didn't give to the model initially, just for training, and then it can predict it by itself. After the training, having all the information, you can train the model, and then just by building the network, you can predict the physical values. Okay. Okay, then I think it's all for today. Thank you for your attention.